Scientists discover first white hole in space. We're all well familiar with the concept of black holes, the ominous daunting regions surrounding infinitely dense points in space with gravity so strong nothing can escape once it reaches the event horizon. But have you heard about the cosmic phenomenon referred to as a white hole? As the name suggested, white holes are the interstellar opposites of black holes, and some theories define them as the other side of the tunnel. And while the name seems pretty self-explanatory, black holes themselves are such difficult to grasp concepts, trying to understand its quantum mechanics is no less a labyrinth. So stick with us while we first explain how black holes work, because the nuts and bolts of a white hole are the exact same, except in reverse. A black hole is the region surrounding a space-time singularity, a point where space becomes time and time becomes space. The circular black body referred to by this name is actually the area beyond the event horizon, the boundary beyond which there is no escape, not even for light. Thus the blackness and thus the name. So how can we see a black hole? Through its gravitational interactions with matter and electromagnetic waves like visible light, black holes can be detected. Stars that orbit a black hole are observed, and by their movement scientists can determine the location of the black hole. If the black hole's gravity is strong enough, it can pull off the gaseous atmosphere of a star and add it to its accretion disk. All of this material that falls into a black hole is heated by friction as it spirals inwards to produce immense heat in the form of X-ray radiation. This heat is of the order of billionths of Kelvin, making it essentially impossible for an observer to get close. Astronomers measure and analyse this radiation to study the properties of black holes. Where do black holes come from? A stellar black hole is formed when a massive star experiences gravitational collapse. When the star's internal pressure is inadequate to fend against its own gravity, usually because they no longer have enough fuel, gravitational collapse takes place, which we observe as a supernova. However, that doesn't mean you have to worry about the end of the world by the sun turning into a black hole anytime soon. Our local stars will go out in a way relatively unceremonious. In approximately another 5 billion years, the sun will become a red giant. Our sun currently powers itself through the fusion of hydrogen into helium in its core. Eventually it will run out of fuel. With no fuel to fight off the inward gravity, the sun will contract and continue to do so till temperature and pressure climbs become critical. At this point, the outer layers of the sun, made up of unused hydrogen and other randomly formed elements, will expand outwards till Mars, engulfing Earth along with it. Perhaps fortunately, we will not be sticking around to watch the final act. Following this, the sun's atmosphere will expand and contract and diffuse and reignite till eventually the atmosphere is ripped apart and all that remains is a fluorescent white dwarf. Our solar corpse will be a swan-like in its beauty. From that melancholy note, let's move on to an intensely bright one. As stated before, a white hole is a polar opposite of a black hole. A white hole is described by physicists as a black hole's time reversal, a video of a black hole played backwards. While the event horizon of a black hole is a sphere of no return, the event horizon of a white hole is a border of no admittance, space-time's most exclusive club. No spacecraft will ever make it to the region's rim. So just as nothing on the inside of a black hole's event horizon can affect the outside, nothing outside can affect the inside of a white hole's event horizon. Scientists have discovered that the light and radiation at energy levels equal to the force with which it goes into a black hole. This has led some to argue that within the year after Einstein opened infinite doors for physics in 1915, Carl Schwarzschild found the solution to do his equation, and his answer lay the first inkling of a singularity. Martin David Kruskal, a mathematician, expanded Schwarzschild's black hole description to span all areas of space and time in 1960, and his new image had a reflection of the black hole singularity, albeit he did not grasp the importance at the moment, as black holes became more understood with a suitable moniker for their conceptual counterparts developed. While this reflection exists in theory, no one can yet fathom how a white hole might be formed. If no event on the outside can affect the inside of its event horizon, It means that the white hole's past is indeterminable. A video of a black hole played in reverse would show it exploding into a nice little star, which doesn't make physical sense and goes against the law that governs all isolated systems. The entropy of such a system cannot decrease. Entropy is described as the level of chaos of matter. Entropy is a count of the amount of alternative configurations for atoms in a system. In other words, entropy is the measurement of uncertainty or unpredictability. The universe can only progressively get messier. That sums up the argument for why white holes may not exist. The black hole information paradox is the argument why they might. How does a black hole die? We don't know. How is a white hole born? Maybe a white hole is the death of a black hole. Physicist Carlo Rovelli said, "The two questions join nicely, but you have to violate the general relativity equations in the passage from one or the other." Since Stephen Hawking discovered the black hole's bleed energy in the 1970s, scientists have questioned if black holes can simply shrivel up and die. The death of a black hole, however, would result in a conundrum. What became of the internal database of everything a black hole swallowed after it evaporated? General relativity will not allow the information to escape, and quantum physics prohibits it from being deleted. While the current generation of thinkers suggests that the information is released atom by atom with the radiation emitted by a black hole, another solution is simply that when the black hole evaporates and shrinks to the point where common sense ends, quantum randomness and the particle level rearranges the gears and forms a white hole, which then belches out all the information the black hole ate up. According to this theory, a black hole becomes a white hole in the instance following its creation, but we continue to observe a black hole from the outside for billions of years. This is due to general relativity's time dilation. Einstein's general relativity theory says that time behaves differently for accelerating and non-accelerating observers. For the matter accelerating toward a singularity, the seconds on their watch appear to pass normally, but for a non-accelerating outside observer, time appears to slow down for the accelerating observer. This effect is called time dilation. What do you think about the existence of white holes? Comment your thoughts below. If you liked the video, make sure to press the like button and subscribe to join us on our space voyage. That's all for now, and we'll be back with another video very soon.